We were talking about linear algebraic equations. We know how to write such a system of equations in the form of a matrix. We know that using the Frobenius theorem, we know how to find whether such a system has a solution at all, namely when the rank of the matrix is equal to the rank of the augmented matrix. And we know how to solve the system using Gaussian elimination, how to bring by bringing the matrix to the upper triangular form. And now what about some applications? Let me show you one interesting application for balancing of chemical reactions. Let us start with a very simple example. Iron plus oxygen give rise to iron oxide. Well, but some stoichiometric coefficients are missing. If we don't know the values, let's write some letters, say A, B, and C, or X, Y, Z if you like, no problem. And now, iron is on the left A times, so the coefficient at A will be 1. Then, no coefficient at B when counting atoms of iron. And on the right, we have 2C. But as it is on the right, that means in the opposite sign as it were on the left. So at C we have -2. And the oxygen atoms, no coefficient at A, 2B, and 3C with minus, so the coefficient at C is -3. Well, and this gives a system of equations that can be described by this augmented matrix. Well, if you want to see the equations, that means that A minus 2C is 0, and 2B minus 3C is 0. Or perhaps you can write A is equal to 2C, and 2B is equal to 3C. A must be indeed equal to 2C, because if we have A atoms of iron on the left, then we have 2C iron atoms on the right. And similarly for the oxygen, if we have 2B atoms on the left, here, and we have 3C on the right, this must be the same. Well, unfortunately, this matrix is already not only in the upper triangular form, it is already in the diagonal form. So this is very easy to solve this system of equations. Actually, you see, we have two equations for 3 unknowns. That means there will be infinitely many solutions. And which one to choose? Well, any non-zero solution will do, but usually we choose small positive integers. Theoretically speaking, we can choose C being t with any real t, just from the mathematical point of view. And then, from this equation, we see that if 2b is 3c, then b is 3/2 of c, which is t. And then a is 2c, but c is t, so this is 2t. This is indeed a solution to this system of equations, indeed for any real t. But we are interested in small positive integers, so we choose To avoid some fractions, we choose t is 2. And then we get a is 4, b is 3, and c is 2. That means we can write this chemical reaction, this chemical equation, as for iron plus 3O2 give rise to 2 Fe2O3. So we have 4 atoms of iron on the left, 4 atoms on the right, and 6 atoms of oxygen on the left, and 6 atoms of oxygen on the right. Well, for this simple system, you may say, well, I don't need such a mathematical tool. I can guess the equation, well, in a few seconds. But consider one slightly more complicated example. Consider the following chemical reaction. Potassium nitrate plus chromium sulfate plus potassium carbonate give rise to potassium nitrite plus potassium chromate plus potassium sulfate plus carbon dioxide. Well, it's not so easy to guess the stoichiometric coefficients for this equation, is it? But we can use the same approach here. For these 6 elements, we can write an equation similar to this, and in the form of a matrix, it looks like that. The first column corresponds to the coefficients at the unknown A. Well, and similarly, the following columns correspond to coefficients at the unknowns denoted by A, B, C, D, E, F, G. Well, and this is again a homogeneous system of equations, so we can write the 0 right-hand side vector on the right. Well, sometimes if we are sure, if we know, if everybody knows that this is a homogeneous system, you don't have to write the 0 column. That gives 1, 2, 3, 4, 5, 6 equations for 1, 2, 3, 4, 5, 6, 7 unknowns. So we expect this system to have infinitely many solutions. Also know that you can think of a division here, because the coefficients to the left come from the left-hand side and are always positive or non-negative, 0 or positive. And the coefficients that come from the right-hand side after this arrow, that means after this bar, are always 0 or negative. Well, we have a matrix, and we can use the Gaussian elimination to bring this matrix to the upper triangle form. I have done this, and this is the result. You can try yourself. Actually, this is only one of the infinitely many solutions. For this system, it turns out that the rank is indeed 6. But we have 7 unknowns, so the difference, 1 in this case, is the number of parameters or number of unknowns for which we can choose any real value. So any multiple of this solution again solves this homogeneous system. Even a 0 multiple, but this is not interesting from the chemical point of view. Even a negative multiple, but this is also not interesting. This is the choice when we get the least positive integers. So in this case, the rank is 6, the number of unknowns is 7, so there is one parameter. What do you think? Can it happen that in some chemical scheme like that, you get a system of equations where you can choose 2 or more parameters? Think it over. Stop me for a moment and think this question over. What if there are 2 parameters that we can solve? Stop me for a moment. Yeah, it can happen indeed. And what does it mean? That means that if we have such a chemical scheme here, then actually it can be decomposed into 2 independent chemical reactions. One of them has its stoichiometric coefficients, which can be multiplied by any number. And the other subsystem has again its own stoichiometric coefficients, which can be multiplied by any number. So we have 2 possible parameters, 2 values that we can choose, 2 unknowns that we can choose. So you see, comparing the rank of the matrix and the number of unknowns, we can detect that the chemical scheme consists of 2 or more independent systems. So this is one nice application of homogeneous linear algebraic equations and the rank of the matrix.